Tell me this. If someone puts two objects in front of you and asks you which one is closer, can you tell or not? Can you identify which is closer to you or not?
We can tell.
Okay. How does that work? How does your brain get information about the distance of an object or a point from your eye? Both objects will be reflecting light into your eye, or maybe they are emitting their own light. That's fine. How will you infer? How do you think that inference is formed as to which object is closer and which is farther? Any idea? Shashank, you unmuted, but I didn't get any answer from you. Anyone? How do you think we can estimate which object is closer to us and which object is farther? You have to come up with some ideas. In every class that I ask this question, they tell some or the other. They give one or another explanation at least.
Faraway things may appear more blurry.
Faraway things appear more.
If they're far away enough.
I'm not able to hear you properly.
Faraway things may appear more blurry.
Blurred. Okay, blurry. No. Is it so? Like, suppose there are, okay, see, there's obviously a screen in front of you, and you consider some other object in that room, which is farther. Just because the object is farther, does it appear more blurry?
Not always.
No, not always. Okay, but still you can tell which is closer and which is farther. Okay, Shashank has given some idea. Okay, others, how do you think our eyes or our brain interprets which object is closer and which is farther? Okay, listen. So as we discussed, there are two different mechanisms by which we can see objects. One is light falling on an object and getting reflected into your eye. Another is the object emitting its own light. Okay, now you can see two dots on your screen, the green one and the yellow one. Tell me, if you are seeing them, that means light from those points is entering into your eyes. If light from the green point and the yellow point, or green dot and the yellow dot, is entering into your eye, tell me, that light, is it reflected light or is it produced by your screen itself? I hope you all are able to see these green and yellow dots. If you're able to see them, that means light from them is entering into your eye. Is it reflected light or is it light emitted by the dots themselves? Anugraha, what do you think?
Light emitted by the dots themselves.
Obviously, the screen is a source of light. Okay, there are something called pixels, you must be aware. Okay, they emit light. Fine. Now, you look at these dots from different angles, or you change your line of view, line of sight. Are you still able to look at these green and yellow dots or not? When you rotate or tilt your screen a little bit, are you still able to see those dots or not?
Yes, sir.
Yes. That means these two dots, the green one and the yellow one, are emitting light. Okay, whatever pixels are there, they're emitting light in many different directions. You look at it from straight in front, you will be able to see it. You look at it from an angle like this, you'll still be able to see it. Means there is light coming towards, light emitted at this angle also. There is light emitted straight. There is light emitted even at this angle. Okay. So the light that enters into our eye, fine. Light is basically an electromagnetic wave. So electromagnetic waves from that green dot into our eye or from the yellow dot into our eye, they're not just one wave. Okay. Those dots A and B are like point sources of light. They emit waves in all directions in front of the screen. Okay, of course, for some screens, you may not be able to see it clearly when you go to that 90-degree angle and all. That is basically some physical hindrance will be there. Okay, but a point source emits light in all directions. We know that. So from the green dot, there will be multiple waves, okay, multiple light waves entering into our eye, okay, like this. You can consider one wave this way. You can consider one like this. These you can say are the extreme ones. There will be infinite other waves in between, okay, infinite other rays of light entering from the green dot into your eye, okay. And you can see that these waves, all the infinite waves, if you bunch them together, if you consider them as one system, they have a certain angle of divergence. This angle, let's call it theta A, angle of divergence of the light entering into your eye from the green dot. Similarly, the yellow dot will be emitting light in all directions, okay. And the light waves that enter into your eye, there are infinite waves that enter into your eye, okay. You can consider the first one like this, and the last one maybe like this. In between these two, there will be infinite other rays entering into your eye from the yellow dot as well. Okay, maybe one of those rays gets blocked by the green dot for that eye, the eye that you see in the diagram, not your own eye. Okay, but other waves will enter the person's eye. Let the angle of divergence of this light be theta B. Okay, so theta A in one case and theta B in the other case. Which angle is greater? Theta A or theta B?
Theta A.
Clearly theta A is greater. If you consider another dot even closer to your eye, okay, you visualize the waves or the rays from that dot entering into your eye. One extreme will be this, the other extreme one will be this. You can clearly see that the angle of divergence in this case is much larger. Okay, this is what helps our eyes interpret the rough distance of an object from our eye. Okay, the angle at which the light enters into your eye. Because depending on the angle at which the light enters into your eye, your eye will have to adjust its focal length. We'll discuss about all this in detail. Your eye will have to adjust its focal length and form an image on the retina. It has to focus these rays on the retina, then only you'll be able to see the object clearly. Okay. Now to bend those blue rays, and make them or bend them towards the retina. Okay, to bend those blue rays towards the retina, the eye will need to have one focal length. To bend those green rays onto the retina, it will have to have another focal length. To bend the yellow rays onto the retina, it will have to have one more focal length. Okay. And as the eye changes its focal length, your brain will interpret that information like we have evolved that way. Okay. Based on the focal length of our eye, based on how our eye has adjusted itself, we can estimate where the object is. Okay. We humans, not just humans, most animals have evolved that way. Okay. And that is how vision works. Okay. And this is a very important concept in optics. Now see, consider that green dot itself. There are some rays. Actually, there are infinite number of rays emerging from the green dot and entering the eye. Okay. Now, if many rays like that enter into your eye, the rods and cones, whatever, like that biology part is there, I think they get excited or whatever, and they transmit the information to your brain. Okay, they send some signals to your brain that there is an object present at a certain distance. It all depends on that angle of divergence. Okay. Now, even if there's no object actually present there, wait, let me just draw a few more rays from that green dot into the eye. Say one like this, one like this. Okay. Now, when rays like this enter into our eye, our brain automatically interprets that there's an object in front at a certain distance. How much distance? Like the point of convergence of these rays, you can say, or the point from where these rays are diverging. Right. Now, even if there's no object actually present, okay, if the rays are simply diverging like this, okay, as if they are coming from a common point, our brain will still think there is something present here. Okay, it is designed like that. Okay, we have evolved like that. So depending on the angle of divergence of rays entering into our eye, we feel there is something present in front of us. Okay, this is the logic behind image formation and all. So if light rays actually emerge from a particular point and enter into our eye, or if light rays seem to be emerging from a particular point and enter into our eye, in both cases, we will see something in front of us. Okay. So if multiple rays enter into our eye such that, or as if they are coming from a common point, we will automatically see something at that common point. Okay, this is the logic behind image formation and all. You'll understand in detail when we discuss reflection, refraction and all. Okay, so what matters most in this chapter as far as your exams and problems are concerned, okay, is finding out this point. Okay, when light hits a reflecting surface or a refracting surface, fine, after getting reflected or refracted, where is this common point from which the light appears to be coming or from which the light is actually coming? The identification of this point is what we do in this chapter. Okay, that is what we call as image location. The point of convergence or divergence of reflected or refracted rays. That is what we call as an image, or the position of the image. So this chapter is all about finding out where the image forms. Okay, how light bends and how the image appears to us. Okay, so yeah, Pradyun and Isha, you have just joined. We were just discussing how our brain interprets information as to how far an object is from our eye. Okay, how far an object is from our eye depends on the angle of divergence of light coming from that object into our eye. Okay, if the angle of divergence is more, the point is nearby. If the angle of divergence is less, the point is far. Okay, that is how we get some idea. And one more thing we discussed is that if light enters into our eye, light entering means what? If multiple rays of light enter into our eye from a particular point, we will automatically think that there is something present at that point. We'll be able to see something present at that point. Okay. Even if light doesn't actually come from that point, let's say it emerges from somewhere in between like this. But all the rays entering into our eye appear to be coming from a particular point, not actually coming, but they appear to be coming from there. Then also we will see something there. Okay, like we have evolved that way. So just when light enters into our eye, the rods and cones, they get excited, they transmit information to the brain, automatically you will see. Okay. So keep this point in mind. What we will be interested in is the common point from which the reflected or refracted rays appear to be passing or are actually passing. Okay, that is what we call as image location, and that is what we'll be interested in. Fine. Next. Reflection of light. See, light basically is an electromagnetic wave. Okay. One of you tell me, what is the range of wavelengths of visible light? Okay, 4,000 to 7,000. Okay, it's not Armstrong, it is angstrom. Okay. Fine. In nanometers, it is 400 to 700. In angstrom, it is 4,000 to 7,000. Fine. So electromagnetic waves of that wavelength can be seen by us. Like when waves of that wavelength enter into our eye, we feel there is something in front. Fine. So basically, it's a wave. When a wave is incident from one medium onto another medium, okay, can one of you tell me what changes for the wave when it goes from one medium to another medium? Any kind of wave, be it mechanical waves or electromagnetic waves, when medium changes, what changes for the wave? Someone said something, but I could not hear.
The
Rishi, what changes for the wave when it goes from one medium to another?
speed of the wave.
Speed changes, correct. What does not change for
The
any kind?
wavelength.
Wavelength will change. Frequency does not change. Frequency does not change. Okay. When light from any wave traveling in one medium is incident on another medium. Okay. In the second medium, the speed will be different and the wavelength will be different, but the frequency will be the same. And generally, when energy is incident onto an interface is nothing but a boundary between two media. Okay. When energy is incident on an interface, that is the separation between two media, generally what happens is some of that energy enters into the second medium, some energy gets reflected back into the first medium. This happens with all kinds of waves, mechanical as well as electromagnetic. Okay. Some absorption or transmission will happen and some reflection will happen. Fine. So if you talk about electromagnetic waves or light, okay, then we call this as reflected light, and the light that passes through the second medium, okay, provided the second medium allows light to pass through it. Okay, media which allow light to pass through them are called transparent or translucent. Okay, suppose the second medium is that kind of a medium, then some light will pass through the second medium, that is called refracted light. Okay, you all must be aware of this anyway. In lower classes also you would have studied. So we'll discuss reflection in detail in this class. Can any of you tell me the laws of reflection?
Angle of incidence and angle of reflection is same.
Okay. Angle of incidence is equal to angle of reflection. Okay. And this is always true, whatever be the nature of wave. This is true for mechanical waves also. Okay. For sound also, this is true, not just for light. Okay. Now, you said angle of incidence is equal to angle of reflection. Rishi, tell me, what is angle of incidence?
So it's the angle at which the light falls on the.
No, you have to be more precise. What is angle of incidence? Suppose a ray of light is incident this way. Okay, a ray of orange light falls on a surface like this. Which angle is angle of incidence in this diagram?
So the angle between the normal and.
Okay. This is the incident ray. And wherever the incident ray touches the surface, that point is called point of incidence. And you draw perpendicular to the surface at that point. Okay, you draw perpendicular through the point of incidence. we call that point as the normal. Sorry, we call that line as the normal. So for this ray, this is the normal. If another ray hits the surface somewhere else, then for that ray, you will have to draw the normal there itself. Okay, so normal is a line perpendicular to the reflecting surface or perpendicular to the surface through the point of incidence. Okay. The angle between the incident ray and the normal is what we call angle of incidence. Okay. And when energy gets reflected back into the same medium, its frequency will be the same. See, reflected light, refracted light, they'll both have the same frequency as incident light. Not just light. This is true for any kind of wave. Okay, even sound. Sound can get transmitted through walls, through doors, you know that. Okay, and you hear echo, means sound can get reflected also. Okay, so sound as a wave, it undergoes reflection as well as refraction. So there also, the reflected sound, refracted sound, they have the same frequency as the incident sound. And the same happens with light. Frequency is same, and when a wave is reflected, it comes back to the same medium, means the speed is also same. And if frequency, speed are same, automatically wavelength will be same. So properties of incident light are same as the properties of reflected light. Only the direction is different. Okay. So if orange light is incident, orange light only will get reflected. And it so happens that this is the reflected ray. And these are basic, you must be aware of this anyway. The angle between the reflected ray and the normal is called the angle of reflection. And these two are always equal. Okay. Next, any other law of reflection? There are two laws actually. First is that angle of incidence is equal to angle of reflection. Next.
The incident.
Tell completely, I just heard the incident. After that, what incident? Okay. Pradyun, I'll answer your doubt. The second law is that the incident ray reflected ray and the normal all lie in the same plane. Like in this diagram that I have drawn, the surface denoted by that black line is actually perpendicular to your screen. Okay, it's like there's a surface perpendicular to your screen, something like this, like the surface of this mobile phone you take. Okay, so ray is incident this way and it gets reflected this way. Okay, so incident ray, reflected ray, this is the surface. Fine. So when you see from the side, it looks like a line. Okay, that's why we indicate the surface with a line in the diagrams. So this is the incident ray, this is the reflected ray, this will be the normal. Okay, the incident ray, normal, and the reflected ray, they'll all be in the same plane. That is what the second law states. Okay. Now Pradyun is asking, is the second law always valid at all points? Yes. Have you learned about any exceptions? We can discuss. Okay. See, wherever the wave is getting reflected, definitely incident ray, normal, and reflected ray have to be in the same plane. Okay, they will be. Fine. So let's solve some simple problems based on these two ideas. If rays are emerging from a common point, then we will see something present there. Okay, our eye will automatically interpret that information and we will see something. Unless there are some defects in our eye, like they're quite common, okay, defects in the eye. And Angle of incidence is equal to angle of reflection. Incident ray, reflected ray, and normal all lie in the same plane always. Okay. Consider this situation. Suppose there's a person's eye somewhere here, and there are multiple rays entering into the person's eye, two of which are like this. One ray is this. Assume it is passing through, okay, this point, let's take it as 0, 2. Okay, that's the point. And at what angle is it? Say some okay, 37 degrees. And another ray entering into the person's eye is entering like this. Or shall we take it like this? Let it be like this. So there are two rays entering into the person's eye. There are other rays also in between. Okay, these are just two of them that are shown here. Let this pass through the point 0, 1 and let it make an angle 53 degrees with the x-axis. Where will the person see the object? Means where is the object located? Object or image, we don't know what it is also. There is light diverging like this and entering into the person's eye. So where will the person see the object? Where means exact position is what I want. Little bit of mathematics is involved. I got only one answer, that is 12 by 7, 23 by 7. Let's see. Can any of you tell me the idea? The calculation we'll do later, but what's the basic concept that you have to use?
You can form equations for two straight lines and calculate the quantity.
Okay. See, there are two rays entering into the eye. Then our brain will show us an object, okay, object or an image wherever these two rays appear to be coming from. So the point of intersection of these two lines is what we are supposed to calculate. Okay, so you'll have to write the equations of those two lines. See, you know point, you know the angle that they are making. So you have to use the slope point form, okay, of a straight line and write the equations of those lines and then find out the point of intersection. All mathematical only. Otherwise, you can use geometry also. Like if you, I got another answer as 20 by 31, 47 by 31, different answer. Let's see. If you enlarge this part, okay, let's just visualize that part of the diagram. So 0, 1 and 0, 2, one line at 37 degrees, one line at 53 degrees. Okay, fine. Assume this is the y-axis. Let this be the point 0, 2. and let this be the point 0, 1. Okay. See, I don't remember how to find out the point of intersection of two lines. So I'll use some other logic. The line passing through 0, 2 is at an angle 37 degrees. The other line is at 53 degrees. Okay. So 37 degrees with the x-axis. Now I'll draw a line like this roughly. Another one at 53 degrees with the x-axis. So maybe like this. What I want is the x coordinate and the y coordinate. So some geometrical adjustments. I'll draw a straight line here. Like from their point of intersection, I'm dropping a perpendicular onto the y-axis. Okay. 3753 actually makes this a right angle triangle, but never mind, let it be. Suppose this distance is y, then this distance is 1 minus y, because the total distance between these 2 points is 1 unit. Okay. This is 37 degrees. This is 53 degrees. Tan 37, which is 3 by 4, is equal to y divided by, okay, wait, actually, fine. Let's call this as x. Actually, I should have taken this distance as, okay, never mind, let it be. So 3 by 4, tan 37 degrees is y divided by x. And tan 53 degrees on the lower side, tan 53 degrees is 4 by 3 is equal to 1 minus y divided by the same x. Now I'll divide these two equations. 3 by 4 divided by 4 by 3 becomes 9 by 16 is equal to y divided by 1 minus y. Okay. Cross multiply. 9 minus 9y is equal to 16y. So 25y is equal to 9. Y becomes 9 by 25. If this is 9 by 25, then this will be 1 minus 9 by 25, 16 by 25. Okay. But the ultimate y coordinate that we want, okay, this points y, at this level, y is already equal to 1. Y coordinate is 1. You have to add 16 by 25 to it. Okay. 1 is 25 by 25. Add another 16 by 25 becomes 41 by 25. The y coordinate of that point is 41 by 25. I didn't get that answer from any of you. We'll see. My calculation could be wrong. Okay. Y is 9 by 25 and y by x is 3 by 4. So 9 by 25 divided by x is 3 by 4. So x becomes 9 4s 36 divided by 3 into 25. These will get cancelled 12 times. So the answer is 12 by 25, 41 by 25. But you all gave different answers. You both gave different answers. Anyway, check it once. Seshank, tell me what are the equations that you got?
3x minus 4y plus 8 equals 0.
Okay, wait. For this upper line, you got?
Yeah. 3x minus 4y plus 8 equals 0.
This is definitely wrong, I can tell, because if you convert it to the form y is equal to mx plus c, it becomes like 4y, I'm sending that side. Then send the 4 back this side. It becomes 3 by 4 into x plus 8 by 4. So you are saying this line has a positive slope. No, this line is going down. It has a negative slope. Okay, so you got the equation wrong. Anugraha, what is the equation you wrote for the first line? Or which method did you use to solve?
Solving them, sir. Same as.
Okay, fine. So write the equations correctly and solve. You should get this answer 12 by 25. I don't think there's anything wrong in this calculation. And Pradyun, Isha, Rishi, did you all understand what I did? Any doubt? Okay, so I just got this idea that we can ask about the position of the object or image also, just based on two rays. So yeah, you just need to know two of the rays, then you extrapolate them in the opposite direction. Wherever they meet, your eye will automatically show you something present there. Okay. Next, let's say incident ray. Okay, this is about reflection. Let's say incident ray travels along the vector 3 I cap plus 4 j cap. Okay, so this vector gives you the direction in which the incident ray is traveling. You have to visualize this vector, and the mirror is the YZ plane. Derive the unit vector along the reflected ray. You have been given the direction of incident ray, and you have been given the mirror, orientation of the mirror. So visualize the reflected ray and get a unit vector in that direction. Okay, 2 minutes. Okay. Anugraha, your answer is correct only. Let us visualize the situation here. 3 I cap plus 4 j cap. Okay. 3 I cap will be to the right, and 4 j cap will be upward like this. It's a vector parallel to the xy plane. So 3 I cap plus 4 j cap is this vector. So it means that the incident ray is traveling in this direction. Where exactly it is, we don't know, and we don't need to know also. Okay, the exact position of a vector doesn't matter. It's just the direction and magnitude that matter. Okay, so this is the incident ray. Now it is given to you that the reflecting surface is the YZ plane. Now your screen is the XY plane now, because we have drawn this vector in the plane of your screen. So your screen is the XY plane. YZ plane will be the vertical plane perpendicular to your screen. So this is the mirror. Okay, and you know angle of incidence is equal to angle of reflection. So making use of that, you can draw the reflected ray. It will look like this. So you can just draw the mirror image of the incident ray. Okay, we are talking about mirrors. Fine. You visualize a normal here. Normal will be the x-axis itself. And the angle of incidence is equal to the angle of reflection. So that's the reflected ray for us. Now we need a unit vector in that direction. What is meant by unit vector? A vector of magnitude 1 unit. Okay. So consider a vector of magnitude 1 unit this way. You need to express it in mathematical form. Okay, let's say this orange vector's magnitude is 1 unit. All you need to do now is write its components, x component and y component. For that, you will need the angle. Now this vector was 3 I cap plus 4 j cap. So this side is 3, this side is 4. So you indirectly know this angle. Call this angle as theta. Then the angle made by that orange vector with the y-axis will also be theta itself. Then its y component. Okay, see, it's very important to visualize the rays, especially while solving optics problems. The y component will be 1 cos theta j cap. And the x component will be, it's to the left, so minus 1 sin theta I cap. Therefore, the unit vector in the direction of the reflected ray, I'll write it as r cap. For unit vectors, we use the symbol cap. Okay, so you can write it as minus sin theta I cap plus cos theta j cap. We still have to find out these values. Okay, so from this diagram, from this right angle triangle, which right angle triangle? The one you see here. Okay, the components. If this is 4, this is 5. Sorry, if one component is 3, one component is 4, the vector's magnitude will be 5. Sine theta, opposite by hypotenuse, 3 by 5. So minus 3 by 5 I cap plus cos theta, adjacent by hypotenuse, 4 by 5 j cap. That way you get the unit vector in the direction of the reflected ray. There's another simple way also to do this, but you should be very confident with vectors. The incident ray vector is 3 I cap plus 4 j cap. No, it is bouncing off the y-axis. Okay, so y component remains same, x component gets reversed. So this vector is minus 3 I cap plus 4 j cap. And how do you take unit vector along the direction of any vector? You divide the vector by its own magnitude. So minus 3 I cap plus 4 j cap divided by its own magnitude is 5. Okay, these two are the same. You can solve it whichever way you are comfortable. Is this clear? Any doubts in this? Okay. You may be asked questions the other way around also. Reflected ray given and incident ray asked, or they can give you incident ray, reflected ray, ask you about the normal. Okay, this is all purely mathematical. You need to form the picture first in your mind or draw it on paper, then use some mathematics to adjust these vectors. Okay, let's discuss that also at the basic level at least. Suppose this is the reflecting surface. Okay, the mirror. Not just a mirror, any surface can be a reflecting surface. Okay, so consider an incident ray like this. Normal and reflected ray. Okay, somewhat like this. Angle of incidence is equal to angle of reflection. One of you tell me an idea. Suppose you are given unit vector in the direction of incident ray. I'll call it as I cap. Okay, I cap means x-axis. Let's not use that term. Let me call it A cap. Unit vector in the direction of incident ray. And unit vector in the direction of reflected ray, let's call it B cap. How will you find out the unit vector in the direction of normal, outward normal? How will you work out the mathematics? Any ideas? Okay, listen. The hint here is that angle of incidence is equal to angle of reflection. Now, A cap and B cap are both unit vectors, means they are vectors of equal magnitude. When vectors of equal magnitude are added, okay, I got two answers. Would it be the resultant of A vector minus B vector? We'll see. To some extent, your answer is correct. So we basically make use of this idea. Suppose there are two vectors of the same magnitude, means same strength, but acting in different directions. Then their resultant will be along their angular bisector, exactly between them. How long it will be depends on how long the individual vectors are. Okay, but it will be exactly between them. This angle and this angle will be equal if the magnitudes of the vectors are equal. Now A cap is a unit vector, B cap is a unit vector. Their magnitudes are same. If you are given vectors instead of unit vectors, also get unit vectors first. Okay. Now, A is towards the surface, B is away from the surface. The normal is not their resultant. But if you reverse the direction of A first, okay, if A is this way, then minus A will be the other way. Let me draw that diagram. This is the opposite of the incident ray, minus A cap. Minus A cap and minus A cap and B cap. If you take their resultant, it will be along the normal. Fine. So normal vector, I'll write it as n bar, will be along B bar minus A bar. Okay, it's the resultant of minus A and B. So B minus A. Okay, so if you just want the direction of the normal, you can get it like this. But if you want unit vector, then you will have to do n cap will be B vector minus A vector divided by the magnitude of B vector minus A vector. Why? Because the resultant of two unit vectors is not always a unit vector. Okay, if you add minus A cap and B cap, the resultant you get need not have a magnitude of 1 unit. So you have to divide that resultant by its own magnitude to get the unit vector. That gives you n cap. Okay, tomorrow I'll send you one worksheet. It'll have questions based on these. Practice them. But is the idea clear to all of you? The idea we are using here is that if you add two vectors of equal magnitude, their resultant will be exactly between them. And we know normal has to be exactly between incident ray and reflected ray. And if you treat them as vectors, they should be going outward. Then you will get the outward normal as the resultant. And if you want unit vector along the normal, then that resultant you have to divide by its own magnitude also. Okay, fine. So see, these are the basic laws of reflection. Angle of incidence is equal to angle of reflection, and incident ray, reflected ray, normal all lie in the same plane. Okay. Based on that, based on these two laws, we should identify how light coming from an object gets reflected from a plane surface and from a curved surface, and where we see its image to be forming. Like when that reflected light enters into our eye, where do we see an object due to that? Okay, where do we perceive something to be present because of that light entering into your eye? Okay. So first, image formation by a plane mirror. And see, don't get misled by this term plane mirror. Any flat surface can be a reflecting surface, perfectly flat surface. Okay, you can treat it as a plane mirror. So it doesn't have to be all shiny and all. Suppose it's a perfectly flat yellow colored surface, that also behaves like a mirror only. Now see, image formation by a plane mirror is actually quite easy. I'm sure you all are comfortable with it, but still we will look at the basics behind all that. Assume this is the mirror, plane mirror. So left side is the reflecting side. Assume an object is kept in front of it, somewhere here. I'm considering a point object. Extended objects are basically collection of point objects. Okay, so if you know what happens to a single point object, then you can easily tell what happens to an extended object also. Light coming from an extended object. Okay. Now, as you all know, you can look at this dot, that blue dot, from different angles. Means light from the blue dot is being spread in all different directions. A single point is called a point source of light. So whether it's emitting its own light or it is reflecting light from something else, it will be reflecting in all directions. So from that point O, there will be multiple rays of light striking the mirror. Okay. One of the rays striking the mirror will be traveling perpendicular to the mirror like this, means it'll be traveling along the normal this way. One of you tell me, what is the angle of incidence of this ray?
90 degrees.
No. Angle of incidence of this ray is 0, because angle of incidence is the angle between incident ray and the normal. Okay, normal drawn through the point of incidence here is this itself. So angle of incidence is 0. This is a very common silly mistake that students make. Angle is supposed to be visualized with the normal. So you have to visualize normal even if they don't ask you to do that in the question. Nobody will ask you to do, but you will have to do. Okay, so this ray strikes the mirror at 0 degrees with the normal and gets reflected also at 0 degrees with the normal, because angle of incidence is equal to angle of reflection. Okay. Consider another ray incident at an angle like this on the reflecting surface. Now, if you visualize the normal at that point of incidence, normal means perpendicular to the mirror, it will be somewhat like this. And angle of incidence should be equal to angle of reflection. So the light gets reflected from that point this way. Okay, so this is one of the rays reflected by the mirror. Now, I have drawn 2 incident rays and 2 reflected rays. Between these 2 incident rays, I can draw infinite other rays as well. Okay, not practically, but we can imagine infinite other incident rays and their corresponding reflected rays. Maybe for this incident ray, it's like this. Okay, even on the lower side of the object, you can imagine, let's say, an incident ray this way. Consider a normal there, and the ray will get reflected somewhat like this. Fine. So there are infinite rays from the object falling on the mirror and getting reflected from it. Now, if an observer is present on the left side, means in front of the mirror. Now we are only considering reflection here. Reflected light has to come back to the side of the object. Okay, has to come back to the side in front of the mirror. Suppose there's an observer in front of the mirror like this. Fine. The reflected rays, they are entering the eye of the observer while diverging. Okay, the reflected rays are going away from each other, and in that process, they are entering the eye of the observer. Then what will the observer's brain tell or brain perceive? It will perceive that there is something present here. Okay, like our brains are wired to do that. We cannot say no to that. Okay, if light appears, if multiple rays of light appear to be diverging from a single point, we will automatically see an image there. Okay, so this is what is the image of that object. This is what we see in the mirror. Fine. And from simple geometry, we can prove that the distance of object from the mirror, okay, if this is x, will be equal to the distance of image from the mirror. Congruency of triangles you can use and prove. We will not spend much time on this. Once we derive the mirror formula, we can easily make the radius infinite and show that object distance is equal to image distance. Okay, so for now, you can just take it for granted that distance of object in front of a plane mirror is equal to the distance of image behind it. Okay. Now look at the diagram and tell me, or from your everyday experience also, you can tell, is light actually passing through the image location? Is any light actually going through this point?
No.
None of the reflected rays have actually passed through the point or the position of the image. They appear to be coming from there. Okay, when we see, when those rays enter into our eye, They appear to be coming from that point I. Okay, the image location. But none of those rays actually pass through that point. Okay, none of those rays actually pass through the image location. This kind of an image, what is it called?
Virtual.
Virtual image. The reflected rays do not actually pass through the image location. Okay, they only appear to be diverging from there. Okay, such an image is called a virtual image. In case of mirrors, no, any image which forms behind the mirror is a virtual image automatically, because rays never go behind the mirror. Rays will get reflected from the surface of the mirror itself. They don't travel behind the mirror. Okay, so if an image is found behind the mirror, automatically it has to be a virtual image in case of mirrors. For lenses, it will be the other way around. Okay, because in a lens, refraction happens, transmission of light. Light actually goes to the other side. Okay, if an image is found there, then that will be a real image in case of lenses. We'll discuss that in detail. So if image forms behind a mirror, be it a plane mirror or a curved mirror, if it is behind the mirror, it has to be virtual. Okay, fine. So for a plane mirror, distance of object in front of the mirror is equal to distance of image behind the mirror. Fine. And because image is forming behind the mirror and rays don't actually go there, that image is called a virtual image. Fine. Let's solve some problems based on this. In optics, drawing the ray diagram, visualizing how the light travels is the most important thing. Okay, like sometimes you may be able to directly get the answer also just by applying the formula, but if you visualize, then you will be conceptually correct. Okay, your answer will be conceptually correct. Okay, suppose there's an object in front of a mirror. Question: if the object moves 10 centimeters towards the mirror, how much does the image move and in which direction? Answer this directly. If the object moves 10 centimeters towards the mirror, how does the image move?
Even the
I just heard even the image. After that, your voice got cut.
even the image will move 10 centimeters.
Okay. So for a plane mirror, object distance in front of the mirror is equal to image distance behind the mirror. Okay, we can make use of that. So initially the image will be formed maybe roughly somewhere here. When object moves 10 centimeters closer, let's say it is here O dash, then the image will be here I dash. Okay, not a big deal. Next, assume the velocity of an object is, okay, say 5 I cap plus 6 j cap meters per second. The YZ plane is the mirror. Derive velocity of the image. Visualize the situation properly and solve. Velocity of object is given to you. The mirror orientation is given to you. You are asked to find out the velocity of the image. See, the object could be on the left side. Then reflection will happen on the left side. You can even imagine the object here moving this way. Then the image will be here moving this way. But in both cases, the answer will be the same. So I'll assume the object is on the left side of the mirror. Calculate or derive the velocity of the image. Anugrah, your answer is not correct. Visualize carefully and solve. Five I cap plus 6 J cap will be somewhat like this. So this is the velocity of the object. Image at the moment will be somewhere here. Okay, now your answer is correct. Rishi, any answer?
Or I'm not sure.
Okay, Rishi, only tell me. Object is moving, so image should also be moving. Now, object's velocity can be resolved into two components. One component along the normal or perpendicular to the mirror, and one component parallel to the mirror. Okay, we know these components also. One is 5 I cap, the other is 6 J cap. So, Rishi, tell me, due to this x component, that is 5 I cap, which way does the image move? Only
It will
due
move towards the image will move towards
towards
the mirror.
the mirror. It will move to the left. And will it move with the same speed or different?
Yes, sir. Same.
Same, because object distance in front of the mirror has to be equal to image distance behind the mirror. Mirror is stationary here. So with whatever speed the object is approaching the mirror, with the same speed the image will approach. So Rishi, tell me, how will you write the x component of the image velocity?
-5.
Good, minus 5 I cap. Okay. Shashank, you tell me, due to this 6J cap, okay, that is one of the components of the object's velocity, how will the image move?
In the same direction.
In the
Upward.
same direction, okay, parallel to the mirror in the same direction. Like this. So it will have the same component 6J cap. That's all. That's the image's velocity. Minus 5 I cap plus 6J cap. Image will be moving along this direction. Is this clear to all of you? Any doubt in this? Right. Okay, Anugraha, just a moment. If we use the formula Vi is equal to 2Vm minus Vo. Okay, I'm not aware of any formula like this, but let's consider what you are saying. Vi, I think, is velocity of image is equal to 2 times velocity of mirror minus the velocity of object. This is the formula that you gave. Do we have to take each I cap direction separately, J cap direction, and solve? Not necessary. You can take it all. Okay. Okay. See, fine. I understand this equation now. I've never used it, but I can understand what you are saying with this. This is valid only for components perpendicular to the mirror, not for parallel to the mirror. Parallel components won't change at all. If objects move parallel to a mirror, images also move in the same manner as the object. But in a direction perpendicular to mirror, if object moves one way, image moves the other way. Okay. So this is valid only for velocities or velocity components perpendicular to the mirror surface. Okay, it's obvious. No, if an object moves parallel to mirror, image also will move in the same manner. Why will it move in the opposite direction? It won't. So this is all valid only for velocity components perpendicular to the mirror. And in this same situation, or okay, let's consider a different situation. Suppose the object is not moving at all. Now we don't know what happens to the image. I can't say it won't move, because if mirror moves also, image will get disturbed. So suppose object is here. At the moment, image will be here. Let's say the mirror moves to the, okay, let's say mirror moves up and down like this. Now when the mirror moves up, the perpendicular distance to the object is still the same. Then the perpendicular distance to the image also will still be the same. Image will form here itself. When it moves down also, image will form here itself. But when the mirror moves to the left, let's say it comes to this position, then the distance of object from the mirror has decreased. Distance of image from the mirror also has to decrease. Image will come here. Okay. And simple geometry, if this is x, this will be 2x. Okay. That is why you got the 2 here. Velocity of image will be 2 times velocity of mirror. Yeah, Rishi, we are almost at the end of the class. So yeah, you can log out if you want. I'll send the recording. So if mirror moves towards the object, image also will move in the same direction as the mirror, and it will move twice as much. Okay, simple geometry. I'll send you one question like this in the worksheet also. You'll be able to derive on your own. And if mirror moves to the right away from the object, image will also go in the same direction at speed twice that of the mirror. Okay, but anyway, I don't suggest you to remember any formulas like this. If you can remember all the formulas in your syllabus, then fine. I personally don't have that much brain. I'm telling this to all of you, nothing personal. But I cannot remember so many formulas, so I visualize and solve problems, and that way it always works. Formulas sometimes can lead to confusion, sometimes can lead to wrong answers also. Okay. Fine, we'll stop it here for today. What we discussed is some basics of how vision works, how we perceive the distance of an object from our eye. Okay, it all depends on the angle of divergence of the rays. And based on divergence of the rays, we can even find out where we see the object. We solved one problem also based on that. Then we discussed laws of reflection and their applications in some cases. Okay. Next class, we will discuss reflection from curved surfaces. We'll derive the mirror formula and apply it in different cases. If time permits, we will even talk about extended objects, magnification and all. Okay. Thank you all. We'll continue in the next class.